In this session, we will begin discussions on how to design tension members. So until now, we have learnt about analysis. Okay, so now it is about design. So in analysis, the configurations are given, which means which angle section or which channel section, how the bolts are arranged, everything is given. And we have to calculate what is the strength governed by different failure limit states. In design, the overall load to be resisted is given, but the choice of the sections and other things has to be done by the designer. Okay. So there are primarily three qualities of any good design. One is that the members that are there should be compact. Okay, so in steel, the cost of construction of steel structures is directly proportional to the weight of the total steel which is being used. Okay, so the rate of the steel also is mentioned, or in the market it is in terms of per kg or per quintal or per ton, right? So the more compact the members are, the better the economy of the design is. Okay. The other thing is that dimensions of whatever members we design should be reasonable in relation with dimensions of the other members, right? So what it means is that if there is a member of size 100 mm, it is not a good idea to connect it to a member of size 1000 mm. Okay, that will be a large disparity in the sizes, and that will not be a good design. Similarly, for especially for tension members, it is better to connect as many parts of the member as possible, so as to minimize the effects of shear lag. Right? We saw that when certain portion is connected and certain portion is outstanding, it causes a shear lag effect, and this effect can actually cause premature failure because the entire section of the member is not being used. Now, in design, there is one more consideration about the slenderness ratio. Okay, so slenderness ratio, which is something which you would be familiar about, is defined as the ratio of the KL, which is the effective length, to the radius of gyration. Right. Now, K depends on the end conditions. L is the actual length, physical length of the member. Right. So this IS 800 table 3, which is shown on the right hand side, this gives limits on the slenderness ratio, right? So it stipulates what should be the maximum allowed slenderness for a particular member. So it is a general table applicable to both compression and tension members. But if we currently look at the tension members, right? So the point number 2 and 5 and 6, these are the 3 points which are relevant to tension members. Okay. So you can imagine that any building where a member is, let's say, under tension, there is a possibility of load reversal. So especially in case of wind and earthquake effects, a member which is in tension can become under compression at any point of time during the load, right? So such members will require a limiting slenderness even to prevent buckling. But in general, there will be many members which are, let's say, always under tension, right? So for these members also, a certain minimum stiffness is required so that the lateral deflection or vibrations which can occur in day-to-day operations, that can be avoided. So if you remember a string, when you tighten a string, it is possible to pluck it, right? A guitar string, for example. So now, it is possible that a string of that kind of an area might be sufficient in resisting a certain amount of load, right? But if it is prone to lateral deflections or vibration by plucking or accidental type of situations, that is not a desirable situation for structural systems. Okay, so that is where some minimum stiffness has to be there, which means some minimum length to area ratio has to be there. Okay, so that is where these are the two primarily reasons of why slenderness ratios are defined or limits are defined for tension members. Otherwise, from strength perspective, there is actually no reason for discussion on slenderness ratios. They become important only for compression members, right? So for tension members, slenderness ratios usually do not govern the mode of failure. They do not govern the mode of failure, and hence they do not govern the strength. Okay, so there are primarily two purposes which we have defined here. So in general, there are three different limits. So 180, 350, and 400. Okay, and this you can see and try to think about why these limits are in that way. Okay, why something is less, why something is more. So try to think about it. If we talk about steps for design, so in general, the input that will be available will be the load demand or load effect, right? So load effect will be known from some kind of analysis or estimate. Okay, either it will be either given or it has to be calculated. So design is also an iterative process. So basically, initially there is nothing, you have to construct a building, so you have to assume certain things. That is just for the initial analysis, right? That is not really design. So you do an initial analysis, then you design all the members, then you do another analysis to ensure that whether the design is safe or not. So it goes on in iterations like that. Lengths and end conditions may also be given. So these are the few things which will be given. So the first thing we will have to do for design of tension members is we can either calculate the required net area or the required gross area. And it is a matter of preference. Some people like to calculate the net area and then extrapolate it by 25 to 50% to get the gross area. Someone may like to directly calculate what is the required gross area. Okay. Now, once the required gross area is known, if there are requirements on the radius of gyration or limiting lambda, right? So limiting lambda will be available from table 3, and the required radius of gyration can be calculated just by inverting the relation that we had in the previous slide. Okay, so depending on length and the end conditions, we can then calculate what is the required radius of gyration for the member. Okay, and once the gross area and the required radius of gyration are known, then from IS 808 we can select a section that has the required gross area and for which R min is greater than R required. Okay, and if you look at IS 808 tables, the radius of gyrations are also given part of the same table for each section. Once we have chosen a section, then we have to do analysis, right? So then we have to calculate what are the strengths in tension of the chosen member with respect to different limit states. So now we have to consider all the 3 limit states of failure: yielding of gross section, rupture at net section, and block shear failure. And once we have calculated the strengths of all of these, right? So if that strength comes out to be less than the demand, then our design is safe. Now, from an economic perspective, if the strength comes out to be much larger than the demand, that is an indicator of the fact that we have chosen a section which is much larger or heavier compared to what we actually need. Okay, so that is also a poor design. It is an uneconomical design, and in both of these cases, the member has to be redesigned, right? So if the strength is less than demand, which means the member is not safe, we have to redesign. Or if the strength is much larger than the demand, which means it is uneconomical, in both cases it is a good idea to redesign. Let's look at an example. So this is 7.11 of the book. So basically it says that select a suitable angle section to carry a factored tensile load of 170 kilonewtons. So in this case, the factored load is given, which means the load safety factor has already been applied. Okay, and actually the configuration of the bolts is also given. Although we will learn about how to decide these things when we do design of connections. Okay, so 4 bolts at the pitch of 60 mm is already given. So the required gross area we can calculate by simply dividing the load by the factored stress. Okay, so the required area comes out to 748. And then we look at the IS 808 tables, and from there we can select, let's say, ISA 7076, which has a gross area of 806. So this is more than 748, which is required. So this might work out, and then we now check whether it works out or not, right? So the strength governed by yielding of gross section, although we are checking it here, but because we are choosing the gross area to be more than the required gross area, right? So this check is actually redundant. It can be avoided. But as a good practice, it is always good to show that what is the design strength in yielding, right? And it is customary to say that whatever force which comes out, if it is more than the requirement, you say okay, so that later on you will not recheck that. Then for the strength governed by rupture of the net section, right? So now in this case we are using the other formula which the code has, which was in terms of alpha, right? So alpha and the net area. So the net area will be gross area minus the area of the holes. Okay, and and in the net area only one hole will be there. So 22 mm is the hole diameter and 6 mm is the thickness. So the net area comes out to this, and the rupture design strength comes out to 176.88, which is also greater than 170. Okay, so this is also okay. We can also do the long calculation for the rupture strength. Okay, so this will require calculation of the gross outstanding area, the net connected area, and the uh, W and WL and BS and LS, all of that. Right, so that can also be calculated. And in general, this usually comes out to be more than the empirical formula which involves the alpha. So this is the rupture of net section. And then we'll have to calculate the strength governed by block shear. So for this block shear, we have to calculate 4 areas, 2 for shear, gross and net, and 2 for tension plane, gross and net. Okay, once we calculate that, we calculate the 2 block shear strengths, because there are 2 scenarios in which block shear can happen. Okay, and if both of them are more than 170 or the demand, then that is also okay. So which means the provided angle is safe in design. Okay, so that angle we have chosen to be provided for the demand of 170 kilonewtons, that is sufficient. So in this session we saw how to design a tension member. Okay, and this was a simple case of low loads where we have to choose an angle section.